coins are too familiar, right? Pick one of these guys.
Illinois State.
There it is.
Bar
That's
Association.
right, yes.
We're all gonna run past the bar
Right.
in our JV.
So today we're going to start chapter 11, talk about Bayesian analysis. Right? And so one goal of this class of mathematical statistics is to look at different ways you can take data and then do inference about things and produce knowledge. And so we've done hypothesis testing, confidence intervals, and some other procedures. And a lot of those have been in the framework of thinking about repeated analysis. Right? You get some data, or you have some a model for the data. This one, yeah, there we go. Still skinny there. That we would have a model for data given some parameters. And we might have framed this as a density function, that has arguments of x for our data and theta as a parameter. Discrete ones might have been the probability that x equals a value depended on some parameter there. And we have NIID observations. So we see x1, x2, up to xn for a sample. And theta is the parameter we want to know something about. And these x's are our data. And so we've been starting with this density model. And then thinking about, well, maybe we could find theta that maximizes this. Maybe we can find some function of x that under repeated sampling is unbiased. And so we came up with different inference methods for it. Right? And we looked at those. We want our confidence intervals to cover, frequently, 95% of the time in repeated experience. And so on. And when we made confidence intervals, we didn't say that there's a 95% probability that the interval that theta is really in that interval, because it wasn't really generated as a probability statement about theta. It was a property, the 95% was a property of the intervals over time, over repeated experience. So not only for our data, but for data that we might see or somebody else might generate at some point in time. And so it has its rationale. It works well in practice, right? But there's another approach that tries to do something different. And Bayesian analysis is one of these approaches. So this theta, this parameter that we'd like to know, is unknown. And in Bayesian analysis, what we don't know, we put probability distributions on. Right? We describe uncertainty by probability statements. So we will put a distribution, a probability distribution on theta. So maybe this would be a little different of theta, another density type of thing, where we express uncertainty by modeling it as a distribution. And so one example today is we're going to have the data x given p to be kind of a binomial experiment. In trial, probability p of success, and p is unknown. So instead of using p hat, sample proportion, or maximum likelihood estimate, or some rationale like that, we're going to put a distribution on p. And the usual, a very convenient choice for a distribution for something between 0 and 1 is a beta distribution, because p is between 0 and 1. And the beta distribution family is very flexible with those two parameters. And depending on what you think before you go around and gather data, based on your prior opinions, these are prior probability distributions, right, for our parameter. Right? So prior to seeing our data, we think about what's going to happen. We look at our past experience and evidence we have from other studies and so on, scientific knowledge, and try to put some distribution that says where we are. Beta can be very flexible. Let's look at a little bit of the code that's on there to illustrate what these things are. So beta has two parameters. Right, so shape 1, shape 2. So I'm going to look at the quantiles of a beta to make a little graph. So the sequence function, right, gives me sequences of values from 0.001 up to 0.999. So I'm going to do the 0.1 percentile up to 99.9th percentile to cover the range. And so for instance, if I just did 0.001 up to 0.009, by that it would give me these numbers, but I'm going to keep going all the way up to 0.999. And get those. This one has a alpha and beta equal 2. These are going to be values when alpha and beta are 8 each. Here alpha is going to be 2, beta is going to be 6. And here's where you can have fractions. They don't have to be, they can just have to be bigger than 0 for this to work out. And then I'm going to plot those probabilities times the beta height of the beta curve over there. And this is what this curve looks like. So it goes all the way from 0 to 1, it's centered at 0.5, and has a lot of probability over there. It's pretty wide, but it says there's less probability up here near 0 and 1. So if I thought that something should be near the middle, but I was pretty unsure, is it 0.2, 0.1, really quite unsure, but kind of in the middle, that would kind of describe that. When their alpha and beta are both 8, right, the beta distribution is more centered. Right? It still goes from 0 up to 1, but again, it's pulled in to the middle a little bit, right? It looks a little bit more normal shaped, but it's more concentrated here in the middle. If it's 2 and 6, things are imbalanced between these two things, and then the probability density would be less. So if you're auditing reports and you think that that there's not going to be that many errors, right? But you're really kind of unsure, and you think the error range 5%, 10%, 20, maybe up to 40, something like that, right? And so before you get into collecting data, if you think that these things generally will pass audit more often than not, and this is the proportion of failures, then maybe that kind of gives some prior probability about where you think it is going to be. You can get funny shapes like the 9/10. That ends up putting more probability out on the tail. So it's very flexible in terms of matching what you could do. If you generate some random values, so here's going to be 10,000 random values from that. The average is 0.5, the standard deviation is 0.225, and the range is basically the whole range there. When we go to 8 and do that, it's still right around 0.5. But now, because those parameters have gotten bigger, the standard deviation has gone down. And the range, you don't get many things clear on the end anymore, but theoretically, there's a chance. It's just, there's not much probability out there and so on. You can do that with the others. You can also get kind of the central, let me go back a couple plots to the 2-2. Here's the 2-2. You can get the quantiles that are at the, say, 2.5 percentile and the 97 percentile. So this distribution, right, we can look at those. We could even do a little bit, make a little line, AB line, a vertical line at these couple of points. Right? And between those is 95% of this probability distribution. So you can get probability less than certain amounts, so 0.10, looks like there's about 2.8% that's less than 10, and so on. But once you have a probability distribution for a thing, there's a lot of ways you can summarize it. You can draw the picture, means, variances, probabilities in certain areas, quantiles, and you can tell me a lot. And if that's your probability distribution, that's the probabilities, and that's what you get. So what we do in Bayesian analysis, right, is we have a model for the data, like a P of X given theta. This is our model. This also could be called our likelihood for the parameter, right? And the maximum likelihood is we just maximize that. Right? We have a prior distribution. For theta. There's a likelihood for theta based on the data. And what we want to do in Bayesian analysis is reverse this. Reverse conditioning. So we have a posterior distribution for the theta, for the parameter, given our data. This is the posterior distribution. For theta. And having this x on this side means that it's given that we've seen the data x. Right? So some people talk about the Bayesian analysis as updating from your prior beliefs about things through likelihood to get new posterior updated beliefs of things. Right? And Bayes' theorem tells us how to do this. Conditional probability, the probability of theta given x, can be written as the probability of theta times the probability of x given theta, right, over the probability of x. That's a statement from conditional probability that in terms of these symbols is true. And then we're going to look at a couple examples to try to understand how this happens in practice. Right? This gets a little bit more elaborate in some cases because what we're going to do, we'll see some shortcuts, but well, this same thing can be down here, right, as a joint distribution. But what we're going to do is actually integrate out theta. We do some math and integrate this out from the joint distribution, and it reduces from 2 dimensions down to just 1. So we're going to do that with the beta binomial scenario. There's a few tricks to doing that. And in some places, graduate schools will have an entire course on Bayesian statistics where you do this a lot. And figure out different ways of doing kind of funny, interesting integrations in higher dimensions and so on. But anyway, we'll figure out how to do it. But it's an updating and a reversals of probabilities from something, a model that says x given theta. If you knew the proportion, I can tell you a lot of what about x should be, to one that says, once I know x, what do you tell me about theta? Right? The person that described such an application in a 1700s article was Reverend Thomas Bayes, who's a philosopher, statistician. Well, he wasn't probably called a statistician, probably called a mathematician at that point, and just general scientist. So anyway, his name got attached to a paper that kind of fell out of favor for a while because you couldn't do much with it besides some smaller cases. Then calculus developed more, and then computing came along, and then high performance computing, and then better algorithms. So a lot more things could be done. There's an International Society for Bayesian Analysis. It's a worldwide organization. They have chapters all over the world. They have sections on different applications of Bayesian statistics. In any case, and So I'm a member of this organization, we've been to some of their meetings, and so Bayesian analysis, I think it really has hit modern times and would be important to learning in large-scale problems. Because to do Bayesian analysis in large-scale problems with a lot of different levels of randomness and data from different sources, you specify probability models for things. You think about models given other things, and then do computing, so that you can summarize the final probability distribution and answer questions. And so you specify models for a lot of things, and then think about the high-performance computing, and it works out. So we're going to look at a simple discrete example of updating probabilities, and go back to the beta binomial one. I need to watch time so we get to do an application. So, so a basic example for this, let's say that the probability that deer ticks have Lyme disease in an area is thought to be 8%. Not all ticks carry Lyme disease, and so deer ticks and carrot, and so say it's about 8%. So the probability that it does not have the Lyme disease, right, is just 1 minus that. So 8% have it, 92% don't. This is like our P of theta, like our prior knowledge at this point, right? And so theta is kind of the state of the world, right? Theta is, having Lyme disease, and then, kind of the opposite of theta is not having the Lyme disease. And so there's kind of one or the other. It's not much of a parameter, it's kind of yes or no in this case, right? And then we're going to test a tick for the Lyme disease, right? And let's say that we develop a test, right? And the probability that the test is positive, given that the tick does have the Lyme disease, is 90%. The test probably goes off antibodies or other chemicals associated with it, or genetic structure that it can detect of the disease. And so say it's 90%. And the probability that we test negative, given that it has no Lyme disease, test negative. Oh, right. So then the probability that it tests negative, that it has no Lyme disease, negative, no disease, right? Well, it must be 90%. And let's see if I actually did this. Right. Right. So given that they have Lyme disease, they either test positive or negative, so it splits like that. Right? And so what's the probability? There can be also a false positive. Right? Some ticks do not have the Lyme disease, but you test them, and maybe they've been around others that have, or there's a similarity of some diseases or chemicals or antibodies that are there. And so let's say 5% of them come up positive even when they don't have a disease. So then probability test negative, given that they do not have the Lyme disease, would be 95%. And so this is really a model, right? This is like our, f of x, theta, where x is the test result. Given the state of the world, either Lyme or not Lyme, depending on which is true, what's the probability of a positive or negative result? Right? So this is like our prior, this is like our likelihood or our model for the world. And now a tick tests positive, right? What is the probability that the tick has Lyme disease? Probability T. What's the chance that it really is infected, given that it tests infected? Right? This would be a type of question that would affect a lot of different medical testing. You test people for AIDS or HIV, what's the chance that they're actually truly positive? Right? Or they come up negative. What's the chance that you're actually truly negative? Right? So the kind of the test result and then the status of the world are these two things. The data that we're going to get, right, are the test results. That's something we're going to measure. And what we really want to know is what's the probability of the positives. Right? So Bayes' theorem can help us with this. What's the probability that a tick has Lyme's disease? That's like theta, the parameter, given that we test positive. And this is like our data x. It's reversing it and giving it the probability that we really want, right? So Bayes' theorem says it's a probability of theta, probability of x given theta, over the probability of x. And so this, in this language, is the probability that there is Lyme disease, a probability of test positive given Lyme disease, right, over the probability of test positive. Well, Lyme disease was 8%. Testing positive given Lyme's was 90%. And probability test positive. Right? In this application, we're going to add two things together. Right? There's some test positives among the Lymes, and there's some false test positives among the non-Lymes. Right? So there's a. Oops. Okay. So point, oh, okay, let me see if I can get this all fixed here. Okay. Let's see if we can get it. I'll touch it. Discharge some static electricity. That's it. So there's 8% that are Lyme disease, and 90% of them test positive, right? And then there's 92% that are not Lyme disease, and 5% of them tested positive. And so this becomes 0.072, and if you add those two numbers over 0.118, and so it ends up being about 61%. So it means that 61% of those who test positive are actually positive. That means that 39% that test positive are not actually positive. So we've updated something from the prior 8%, right, through the likelihood, through the data. Now we come up with 61%. We moved from 8% to 61%, so that's a huge increase. But it's not 90%, 99%. It's not, it doesn't jump all that way. Right? You might think it would because there's a 90% testing positive rate. But you're trying to pick out something that's kind of unusual, right? Only 8%. Most of the ticks that test positive. This number here is 0.072 for this one. This one is not trivial. It's 0.046, right? So 7% tick of those that test positive. So anyway, it's that kind of split. So it updates information like that. So if you had a different, say the tick tests negative, right? That's our data. We could do the same exercise and look at the probability of that there is no Lyme disease, that is there Lyme disease? What's the probability of Lyme disease given that you test negative? Well, there's 8% with Lyme disease. Reversing it then, only 10% of those test positive. And in the denominator is going to be the probability of test positive, so 0.08, 0.10. And then there's 92% who do not have Lyme, and of those, 95% test negative. So when it's like this, that ratio ends up being quite small. So this ends up being about 0.009. So if a tick tests negative, there's a low chance that it has, a very low chance that it has Lyme disease. There's only 8% anyway. And most of those that are negative, test negative, do not have Lyme's, test negative anyway. And so depending on what you're conditioning on, what the data are, it tells you different things about the parameter, about the state of the world. Right? Sometimes these things in a case like this, where we, in introductory statistics, we make a little probability tree. Here's kind of our theta. Either there's Lyme or no Lyme disease. And so this one was 8%, and then there's 92% here. And then you either test positive or test negative. And this was 90% and 10%. Right, so there's 0.008 if you multiply that way. And then 95% tested negative, 5% tested positive here. And so that, what are those numbers? Anyway, then this was 0.0, so that's 0.72. 0.720, 0.72. 0.72 here for this. And so, for instance, when we wanted that test negative, right, here are the two endpoints that test negative, and this probability is 0.92 times 0.95. But anyway, so we have a prior on what we think the state of the nature of the world is, our opinions. And then we have this model, and then we update the probability. Some people criticize Bayes because you got to get that prior probability from somewhere. That's a subjective part for some people, and they don't necessarily think you should be objective like that. Let's try to do something that tries to avoid that, but it obviously gives you some way to update of things for data. And so in the case that our data come from a binomial distribution within trials and a probability of success p, right, so this is our model. So the probability that x equals something is a binomial probability formula. Right, n choose x, p to the x, 1 minus p to the n minus x. P is a probability between 0 and 1. And x is a count, 0, 1, 2, right, up to n. And p is this parameter. Right, so we're going to put a prior distribution on p. And we're going to use a beta distribution. This is a prior distribution. The probability distribution for a beta is continuous, but we can mix and match these things. It works out. The probability, so maybe I'll write f of p, so we don't get too many p's. The density for p, the function that gives that curve that we looked at in the pictures, can be expressed a few ways. But there's a gamma function, which is a mathematical function. It's a function of the two parameters there. There's a p to the alpha minus 1, 1 minus p to the beta minus 1. Now to do this application, you don't need to understand the gamma functions in great detail. We'll show you how the calculus works and what the final answer is. We're more thinking about the reasoning of starting out with prior and then a likelihood and putting them together. And so what we want to do is, this is, I guess I could put it here, right, conditional on p. Given p, this is the probability of x. Right? And here's the probability of p. Now, we're going to observe x. You're going to flip the pigs a few times. Right? And we're going to see how many times they land on their snout or on their feet or whatever you want to whatever we decide to do. And then we say, what's the probability? Right? So now we observe a value, x equals x, and we want the probability of p given x. And I write this as a little f because it's going to be a continuous probability density function. To do that. Right? So what is that one? Well, let me tell you. Oh, yeah, I didn't have you get one of those. Which one you want there? Yeah. It's well, let's see. We can build this up a little bit. Following, so there's going to be a density for p. there's a probability that x equals some value given p. And this is mixing kind of a continuous, discrete one, so they're a little different notation, but it's okay. And then a probability that x equals some value in there. In the numerator, we'll have a gamma alpha plus beta over gamma alpha, gamma beta, p to the alpha minus 1, 1 minus p to the beta minus 1. And then you get this n choose x from the binomial, choosing x successive out of n. There's a p to the x, 1 minus p to the n minus x. That's all in the numerator. Of this thing, right? These get a little bit longer to write out, but it works out, right? The denominator is that same thing, but you integrate out p. Right? The probability of x, that x equals something, is going to be integral of f of p, the probability that x equals x given p dp, and that's too small to read. I'll rewrite that. Right. What we're doing with the f of x is we're going to integrate out of the density of p, the probability that x is its value given p dp. And so this thing here, when they're multiplied together, it's like a joint density of p and x together. And integration means you average over or take out one of the dimensions. Right? So that's what we're going to do there. We won't. There's ways to do this, but it's mostly through recognizing that this is done in probability, really through recognizing different patterns. Right? And so one thing we're going to do is just kind of go back to this thing and look at things. Let me get this out of here. And so the thing that's, I'll just write the probability of x down here. Before jumping to next, right? Let's look at a few things here, right? How could this numerator be simplified?
Combine the p's.
Some is p to a power a couple times, 1 minus p to a power a couple times. Right?
And then the gammas and the n choose x are constant.
Yeah, relative to the p's,
Yeah.
those are constant. So they can be written, let's just write them out here one more time. And then n choose x. And then we'll write the p's. There's alpha plus n minus 1, and 1 minus p to the beta plus n minus x minus 1. And I've written it this way, right, to kind of preserve that beta structure, the beta distribution structure. Because there's p to a power minus 1 and a 1 minus beta to a power minus 1. That's there. Over the integral of this same thing, right, it's exactly the same thing than dp. Right? So one thing that's going to happen is these constants are sitting down here too.
Cancel.
Yeah, and so because it's integral dp, these things don't have p. These are just constant multipliers. These are combinatoric multiplier type things. Right? And so they just cancel. Right? And so what we end up with, I'm not going to write that there. So the density of p given x ends up looking like p to the alpha plus x minus 1, 1 minus p to the beta plus n minus x minus 1. And there's an integral of that same thing, dp, that's down there. Well, this is something called a beta integral, which can be written as gamma integrals. And with going through the math like you would in a probability class, this thing ends up being gamma of alpha plus beta plus n, gamma of alpha plus x, gamma of beta plus x minus n, that there, and then p to the alpha plus x minus 1, 1 minus p to the beta plus x minus, n minus x. There. N minus x plus minus 1, sorry. That same thing. So this thing, and p is between 0 and 1, right? Range still the same as before. So this is a density of a new beta distribution. Right? It's still p to a power, 1 minus p to a power, both minus 1, with certain gamma multipliers out there that would correspond to what you would get for a beta distribution. So it is a beta distribution. P given x has updated to become a beta distribution. So the conclusion is that P given x has a beta distribution, and its parameters are alpha plus x, n plus, well, beta plus, you can write it either ways, beta plus n minus x, and that's the distribution. So for with real numbers, right, you could then do a calculation of what those things are.
So we've updated our model.
Well, it's updated the probability statement. Right? So P before was a beta that just only had alpha and beta. Right? The expectation before P was a beta distribution with alpha and beta. Right? The expectation of P, this be called the prior expectation before data, is alpha over alpha plus beta. How that goes. So when alpha and beta are the same, it's 50-50. Now the mean is 50. Right? Now the expectation over here is the posterior mean, right? The mean after seeing the data, and it's going to be the alpha plus x over the sum of these two things, which is alpha plus beta plus n. And so that's the posterior mean. It's going to change depending on what your data is. There's an interesting way to write this in this case. Right? That if if you write alpha plus beta times alpha over alpha plus beta here, and then you write n times x over n here, alpha plus beta plus n. I guess I'll take the whole line over here. And I'll put this over here. That the posterior mean in this case ends up being, you can think of it as a weighted average of two things. One thing is my sample proportion. This is usually what we call p hat in there. And this other thing, right, is this prior mean. So it looks like we've combined information, right?
So it's kind of like when we got the p hat before, we didn't have any prior observation.
Right, so when you chose these alpha and betas before, right, you can choose them to match a mean and a variance, and I think we'll go through that on Wednesday to match things up, right? To kind of express what you think going into it. So let's look at the pigs, right? So maybe you've thrown these pigs around a little bit. These come from, I don't know, these were marketed back in the 90s, you know, teaching statistics and getting people to do things, because flipping a coin or a six-sided die is too familiar, right? It's everybody's going to say it's 1/2 or 1/6 or something. But you know, these can land many different ways, right? So they can land on their sides, on their backs, they can balance on their snouts a little bit there, right? And different things stand up. And so let's choose one of these. Right? How should the pig land? Right? What are you interested in? What do you want to count? What outcome do you want to do? On its feet, standing up on its feet? So on feet, okay. So before you do any more experimenting, right, we need to come up with some prior distribution, right? Do you think this is a high probability event, a low probability event? Right?
Low.
Pretty low? What if we do that kind of beta, how low? So beta 2.6, right, the mean, the prior mean for this, right, would be 2 over 2 plus 6, 2 over 8 would be like 1/4. Maybe that's a little bit high, but this is with only kind of 2 plus 6, 8 so-called kind of prior observations. You can imagine having 2 flips that come up, yes, that land standing like this, and 6 that land some other way. That's kind of like what the information content would be in that, right? So if that's our prior, now let's gather data. So everybody flip the pig, say, 8 times. And then you can tell me how many times it comes standing up. Right? So do it 8 times, and we'll get our data. Or is it easier to do it 10 times? So let's do it 10 times, okay? Everybody doing it 10 times, right? So how many times did you get it? 0? Okay.
1.
1 time, right? How many times?
1.
1. 3?
Yeah.
Right. How many times do you get it? 0. Right. That, a little bit more. What did you get?
2 times.
2 times. I'll do it over here. 2 and 8. And both in 0. Right. 1.
0.
0. 10 and 0. Okay. Right. So we have a lot of data, right? So 1, 2, 3. Okay. So we get 1, 2, 3, 4, 5, 6, 7, 8, 11, 12. So n is 120 in all. Okay. And let me clean this mess up here. How many yeses? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. X equals 11. So n minus x is 109. Right? And we started out with a beta distribution, 2, 6, I said, right? That's the prior. Right, so then the posterior, given that x equals 11 and that we had 120 total, is going to be a beta, right, 2 plus 11, and then 6 plus 109. So this is a beta, right, of 13 and 115. Right? And so this mean is 13 over 1. Have I added things up correctly? 115, 1, so we had 8. Oh, so this is, 128. That's what it should add up to. 13 over 20, 28. That looks like less than 10%. This prior mean was 2 over 8, or 1/4. So we've adjusted, right, our probability distribution. And it's become a lot more narrow, right? So we could modify this code. So we started with 2 and 6 as our prior. And then we plot something. 2, 6, 2, 6, 2, 6. So this is our prior, like that. And then we update things. If I'd written a function just called alpha and beta, it would be much easier to change these things.
13.
I'll just do, I won't change it there, just make it 13 and 115 there. Right? I'll take that out, take that out, so it's 13 and 115. And so maybe I can put these points, or let's just plot it, right? And so it's like this, right? So what was the previous one? Try to put these things on the same thing, like 0 to 8. If this is on the EX limits, are kind of like they had before, kind of 0 up to 0.6. This one was actually 0 up to 6.7, 0.7. We'll see this thing kind of more. Right, so we've really gone from this prior, let me get these right after each other, and then this thing. So we went from this prior distribution, that's fairly diffuse, right? And we've got the 120 observations, and we've switched to this prior distribution, which is pretty tightly focused. And we can report a 95% posterior probability interval, right? So we'll say that the quantiles for a beta at the 0.025, 0.975 for 13 and 115 parameters is the 95% posterior interval. And so we're 95% probability that theta is in this interval. Because this is a distribution for, or P, this is a distribution for P, given the data, right? So 0.056, so 95% probability that P is in this interval, 0.0556, 0.0556 up to 0.159. Right, and so that's where the probability is. If the data had been different, the interval would move, right? P hat, if we did maximum likelihood, with 13 over 120, the posterior mean, also, anyway, 13 over 120 for our data, 0.108. The posterior mean, where we had 13, no, we had 11, right? That was, sorry, we started with 2. The posterior mean is not that, it's 0.09, because we didn't have, 2 of those were prior observations, so this would just be 11, right? And then it's so. But anyway, so if the data were different, based on that, proportion test with 11 out of 120. Right, let's not do the continuity correction now. Oops. A 95% confidence interval goes from 0.052 up to 0.157. 0.157, 0.052. So it's a little bit lower, right? This one's a little bit higher because our prior mean was a little bit higher, right? So our prior guess was a little bit higher, so it kind of pulls it up there. And so, yeah, this is a 95% confidence interval. It makes use of the sampling theory, the sampling error, sampling distribution, whereas this one goes to this Bayesian calculus to get a probability statement, right? And many people like the probability statements. It is a probability statement. And others will say, well, I didn't think your prior probability distribution was any good. I didn't think it was going to land on this, a quarter of the time. That's ridiculous. And it should have been much smaller, right? And so if your prior is much smaller, it's going to move that. And some people don't like that different people can come up with different conclusions. Well, guess what? Different people can come up with different conclusions anyway, depending on what they believe is going on with the experiment. Was everybody flipping the pig the same way, the same height? Was it all, was some landing on paper? You know, if it was landing on the carpet, it'd probably come out different, and things like that. And maybe thrown with greater velocity, it's harder to, you know, land a certain way. There's many things that affect it that are not much wind in the ears, so that's not something. What happens with, if there is a truth, a real probability in there, and we kept doing this, and kept getting more and more data. If we did it 10 or 20 or 40 more times, the difference between the maximal likelihood and the probability estimates shrinks to 0. Because what happens, for instance, in these means, right? Where's my formula? Right? What happens in these formulas as the sample size gets big, or as the sample size gets big? Well, if you divide both of these things by kind of 1 over n, well, these things like alpha plus beta over this essentially goes to 0 as you get a large value of n. This, n over that, essentially goes to 1. And you're just kind of left with p hat right there. So as the sample gets bigger, it dominates a single prior observation. It becomes much more like the likelihood. And there's similar results that Bayesian estimates in large samples are normally distributed, just like a likelihood has a normal curvature on it. And so as the sample sizes get larger, you get less impact of the different prior opinions. Some people also, so-called objective Bayesians, try to do one to kind of get set up standard priors that everybody could use. So if each of these things is like 1/2, it has some nice properties in some distance sense. And so people set up things that make it possible for people to do this, right? To use it and be less worried about choosing a prior opinion. But many Bayesian applications get done in areas where it's very hard to get data. Like, what's the chance you have a nuclear power plant fail? You don't get much experimental data, right? And you have test runs of different pieces, different designs, different evaluations, which start to show problems, and a lot of science, right? So you take the smallest amounts of data where you have, and you link them together with probabilities, and then go through a big calculation like this. And it's done through simulation, and it's much more complex. But the goal is still the same. Come up with this posterior distribution that then you can summarize, and you can tell me where the parameter is. So, but anyway, that's kind of introduction to Bayes analysis. We'll look on Wednesday and Friday. We'll look at a couple more examples of doing this conversion and looking at how to use it with data and doing the contrast of it. I'll leave the pigs back so I can use them in the future. So. Thank you. And if you're really interested, I can help you order your own set. Thank you. It's fine. Right, thanks, Gordon.
So if you pick a random prior mean and repeated it again and again, we get the likelihood. Right, because if you keep on repeating this for sample size that gets big, you get the same, you get like the p-hat.
Right.
So I guess there'd be no point to that.
So it's there is an updated problem, right? So if you got new data, you wouldn't start at this old prior. You'd start here. And this would be your new prior.
Yeah.
And then you get new data, so you'd add another x and another n minus x, number of success failures. So we could have done this one by one. One student, add another one in, add another one, and you keep learning. And as the sample size gets bigger, the prior gets more narrow generally. It will shift depending on how things go randomly, kind of narrow on whatever the situation is. So, have a good one. Yeah.
Okay.
Yeah. right, thank you. That was late. Thanks for getting it in. That's great. Okay. Bye, Connor. See you.
Thank you.